So variable coefficient equations. So the best thing about differential equations is repeats, but different situations. So for example, now that we know how to do this situation, and the special case when this is 0, well, we only talk about if these are functions, or sorry, constants. Now we're going to talk about, well, what if they're functions themselves? So now it's a of t, b of t, and c of t equals f of t. Okay, what are these situations in scale? So because these are so particular, they have an actual name for them. We'll talk about that in a little bit. But, this theorem basically says if it's possible, we can actually find it. It's just a situation where, we can actually find a solution to these particular equations. All we really just do is divide over the a of t to everything. And therefore, g of t is just a division of f of t over a of t. Same thing with p and q. But, once we'll get there, we'll get there. What's the most important thing is something called Cauchy-Euler equations. So this is the actual type of equation we're going to be dealing with for now. Okay, these are linear second order equations of the form like this. Okay. So the reason why they're second form is because, well, obviously it's y squared or y double prime, but it's also t squared going down. Okay, so we have a functions in server t, but it's always in just second order, being squared, 1, and then 0. So it's kind of like the second order proper. Same with the y double prime. So these are called Cauchy-Euler equations. They're very popular when it comes to the actual portion, hence the reason why they actually have a name for it. All right, so the question is, how do we solve for things like this? Okay, so a lot of algebra again when it comes to it. However, it always goes back to the characteristic equation. Okay, so the first thing we do is solve for our characteristic equation. And because we have functions and now just constants, our characteristic equation is always going to look like this. Okay, so just like everything else, we have three situations. If we have unique solutions, therefore our y1 and y2 are just going to be t to the r power. And then where the other r, let's call this r1 and r2. If we have imaginary numbers, when it comes to our characteristic equation, it's going to look like this for y1 and y2. And then finally, if we have repeated ones, it's same as what we do for the district one. However, this ln of t is added on top of it. Okay. So let's just put this to practice, each individual case. So find two linear independent solutions to the equation. Okay, and you'll see why this is important in a little bit. All right, so we'll just follow the process we have here. So first, well, let's just write down. So we have a is equal to 3, b is equal to 11, and then c is equal to negative 3. So if we follow this process and we just plug it into our characteristic equation, it's going to be 3r squared plus b minus a, so 11 minus 3, r minus 3 equals 0. So simplifying this a little bit gives us that. So hopefully we can factor this instead of using the quadratic formula. And it looks like we can. So two things, you multiply, give you a negative 9, add up, give you 8. So it looks like maybe 9 and negative 1. So looks like those are our factors. Okay. So therefore, r is equal to negative 3, and r is equal to positive 1/3. Okay. So we have distinct ones, which means our solutions is just t to these powers themselves. So t to the 1/3 and t to the negative 3 power. Okay. So let's try some more using this proper Cauchy-Euler equations in these situations here. Okay, so in this case, a is going to be 1, b is is 5, and c is also 5. All right, so we go back to our equation. So it's going to be here. Actually, I'll just follow it up here. I have a. There we go. This is what I was looking for. I'll leave it here while I follow this format. Okay. All right, so 1r squared, so just r squared, plus 5 minus 1, r plus 5 equals 0. Okay. All right, so that gives me r squared plus 4r plus 5 equals 0. Okay. And I don't think this actually factors. Five and 1 are the only thing that work here. Nope. So probably going to be imaginary numbers themselves. Okay. All right. So probably going to be looking at here. So after, again, simplification, we end up getting r is equal to negative 2 plus or minus I. Okay. All right. So according to our equation, if it's imaginary, we have a and b. So in this case, this is a, this is b. Well, number of the front, so a will be negative 2, b is going to be 1. And we're just going to write them just like that. So my first one is t to the negative 2 power times cosine of b, which is just 1, so it'll be ln of t. And the second one is just a copy-paste, but instead of cosine is just sine. And there we go. So let's try the last example down here. All right, so in this case, a is going to be 1, b is going to be 1, and c is going to be 0 in this case. Okay. All right, so it'll be r squared plus 1 minus 1r plus 0 equals 0. So that goes away, so we just get r squared equals 0. So r is 0 is the only root we have. Okay. Now the best part is it's actually repeated, technically, right? So we do have a repeated root. So according to our equation, repeated roots look like that. So t to the 0 and t to the 0 ln of t. So t to the 0 and t to the 0 times ln of t. So in shorthand, 1 and ln of t. All right, so on that note, we have a lot to talk about now when it comes to this section and how things are reorganized and redone. Now, the reason why I say that is we actually introduced something called the Dvorsky in this section, and we use it a lot more going forward in chapter 5 and 6. So the Dvorsky is actually the determinant of a 2 by 2 matrix, we'll talk about farther up, of its derivatives. So how this works is we first find, y1 and y2 are solutions. Take these derivatives and just take the determinant of it. Okay. Now, if this determinant is 0, then we say then y1 and y2 are linear dependent on each other, which means it's not good, right? So which means they're probably not solutions to the actual differential equations, which is a big problem. Okay. But if it's not equal to 0, then we have an opportunity to do so. Okay. So again, this is a quick little understanding how to show that these two things are not linear independent of each other, is just doing the Dvorsky of it. So fun little fact there, a little hint going there. However, if we do have them, here's going to be our general solution for a non-homogeneous equation of this format. So again, g of t is the division of f of t over a of t, right? Just divide this over. So given this situation, remember all this is being divided by a of t. This is our particular solution, and this is our homogeneous part. So same situation we've done before, nothing really new, but we just have a different situation happening. Okay? Now the problem is, well, how do we actually do that, right? How do we actually find a particular solution now, because now these are different functions? So we now rewrite our variation parameters based off our Dvorsky and how to do that. Now, if you're wondering, well, what's the big deal about the Dvorsky being 0? This is the biggest thing possible. Because our theorem here says if y1 and y2 are linear independent solutions, key thing, to the homogeneous equation, therefore, we can find a particular solution to this part, again, using the variation parameters, right, using either solving for the system, or the key thing is we can rewrite now what actual variation parameters are based on the Dvorsky, this here. And this is the reason why the Dvorsky cannot be 0, because we're divided by 0, which is not allowed. Okay? So this is an easy way to see if you actually have linear independent solutions, or you just check them together, right? So if you're asked, are these two solutions actual solutions, or linear independent solutions, just check the Dvorsky. Because if they are, this will work. If they're not, you'd be a big problem because this will end up being 0, which is a big no-no itself. Okay. So therefore, we have a very interesting reduction of order process. Is if y1 is a solution, well, how do I find another one without having to do all of this work? Because sometimes, solving for the homogeneous part could be a painful thing, right? So if we're already given 1 to begin with, this is a nice theorem to find the other one. So again, if y1 is a solution, not 0, obviously, to the homogeneous equation, then we can find another one using this equation, okay, where p of t represents this p of t in the equation itself, in a differential equation. Okay. Now, I'm not saying this could be fun to actually integrate because it's a double integral, but it's an alternative to find a different one, and this guarantees you linear independency, which is the best part. Okay. So, a lot of stuff happening here. Let's try this out. So how will this work out with the best part to deal with? So here we're given y1 to be equaling t is a solution. Find any solution that is linear independent, so any of one. So let's just do easy of the two. Let's just use our equation. We just talked about that. So to find our equation, we need a couple things. So we already given y1, so that's done. That goes here and here. We just need to find p of t. So p of t here, we write there. So therefore, according to our equation, so y2 is going to be the integral. Oh, actually, before I go there, it's equal to y1, which is just t, times integral of e raised to the integral of negative 1 over t over y1 squared, or just t squared dt. Put that dt there as well. So this is nice. This is ln of x. So we'll just, slowly break this down. Okay, so far so good. Okay. Now, here's a fun little fact. There's a negative out here as well. So, in our equation, this ends up being positive. Which is nice because we don't have to bring the power anymore. They just straight cancel each other out. which just cancels to, again, 1 over t. And we just did this, the integral 1 over t is ln. So it's just t times ln of t. So a solution to this part will just be t times ln of t. Which is interesting because we just talked about this. This represents a double root. So we just found a double root to our homogeneous equation, which works. Now, if you wanted to check, that these two are linear independent, well, what do? Find the Dvorskian and make sure it's non-zero. That's it. As long as it's not in zero, we're A-okay. Nice little check there. Okay. All right. So find the general solution of this one. Okay. So this one's a little bit more finesse when it comes to it. Okay. So I'm going to divide everything by sine of x, or sine of t in this case. So divide everything by sine of t. These go away, and I'm just left with, and then cosine over sine is cotangent. Now, unfortunately here we're not given y1. We actually have to find one. Okay. But since it's, cotangent, we have some options. It's either going to be sine or cosine. It's going to be one situation or a combination of either one. Okay. So hopefully we guess right. Which is just cosine. So if we take the derivative, okay. All right, so now we just plug in all this into here. So we get negative cosine t minus 2, and cotangent again was cosine over sine, which is nice because this one is negative, and this is cosine. So those cancel. Negative, negative, positive. So I get negative 2 cosine plus 2 cosine does actually give you 0. Yay! We checked. We actually guessed right. So therefore, one particular solution is just cosine t. So if you guess wrong and you use sine, that's okay. Then you just know the other one's actually correct, which is kind of nice. So again, the best part is all we care about is we found one, because now we can use our equation to find the other one. Okay. So this is again going to be a little bit trickier. So to find y2, so this is going to equal to cosine of t times the integral of cosine squared, and on top e. Now this is where I go back to it. All right, let's see. Yeah, I'm going to keep this here. So we're going to use this as p of t. This is the second reason why we want to keep that there. Like that. Okay. So cosine, actually, the integral of cotangent, which is nice, is just ln of sine. Okay. All right, bringing this here, and then e's cancel. And I'm left with this. Okay, so there is a trig identity that's used here. And this trig identity basically just breaks this apart. You bring this down here, and there's identity is basically 2 sine of x is equal to sine of x cosine of x, I believe. And just straight that, just do that identity, and you end up getting the integral of secant squared, I believe, and it just gives you this at the end. So this process will be y2. If you want, you could distribute it to be cotangent squared or cosine squared over sine, end up being that, but not a big deal. But our goal was to actually find a general solution. So our general solution will be the first part we got. So c1 cosine of t plus the other one we got. So c2, and I'm just going to put this together. So the nice thing is the c2 and the negative 2 just get engulfed. It just goes away. And there we go.